So for the rest of the time in this section, all we're going to do is just look at examples where we look and try to work through problems with respect to Greene's theorem. So let's say we have a line integral of this ugly looking line integral in this case, and C is bounded by two parabolas, y equals x squared and x equals y squared. Another way to write that is square root of x equals y, which might be a little bit easier to think of for us to think of in terms of solely x. All right, now the first thing we want to do is we'd want to try a parameterization if at all possible. However, a parameterization would mean that we'd need two separate line integrals. And not only that, but I'm thinking about maybe like something like this, e to the t or e to the root t, and I'm just thinking that it might not even be possible for us to evaluate this, okay, without using Greene's theorem. So if we construct the region, here's what we get. Here's our quadratic, here's our root function, and then here's our quadratic. And notice that clearly it follows this counterclockwise, i.e. positive orientation. And we don't have to go through the algebra of this, but we know that that's the point 1, 1. And even though my drawing's not that good, this is the origin. All right, so the first thing we always have to do with Greene's theorem is that we have to show that it indeed exhibits positive orientation over a closed region. The next thing we're going to do is we are going to bind the regions parametric, or as a type 1 or type 2 region. In this case, I think it could be either type 1 or type 2. Let's just make it type 1 by going up and down. Remember, this is y equals x squared, and this is y equals square root of x. So if I were to put this in terms of a type 1 region, y would range from x squared to square root of x, and x, not surprisingly, would range from 0 to 1. Okay. Let's define our function p and our function q. And those are going to be the functions we need. There it is. This is q. All right. Those are going to be the functions that we need to throw into the integral. All right. And this one's going to turn out really, really nicely. All right. So the partial of q with respect to x, so derivative of 2x is 2, derivative of cos y squared is 0. The partial of p with respect to y, that's going to be 1. All right. Greene's theorem says we just subtract the two and then set it up as a type 1 or 2 region. And so we can say that the closed region of the original integral y plus e to the root x dx plus 2x cos y squared dy is going to be equal to now a double integral of x squared to root x, 0 to 1, 2 minus 1 dy dx. All right. And clearly this becomes a very easy integral to evaluate. All right, so we're just going to go through. By the way, this just becomes 1. I know you all can see that. All right. So we just get y that goes from x squared to root x dx. We're going to substitute and subtract, so that's going to be equal to integral 0 to 1 of root x minus x squared dx. We're going to take the antiderivative, so that's going to be x to the 3 halves over 3 halves minus 1/3 x cubed from 0 to 1. And essentially, it's going to end up being 2/3 minus 1/3. All right, when we substitute, so that's just going to give us 2/3, because we substitute 1 back in and then multiply by the reciprocal minus 1/3, and that's just going to give us ultimately a value of 1/3. All right, clearly much easier to evaluate if we utilize Greene's theorem. All right, so a third example of Greene's theorem. So let's say we have this let's say we have this line integral, x cubed minus y cubed dx, x cubed plus y cubed dy. C is bound by two circles, x squared plus y squared equals 1, x squared plus y squared is 9. Graphing the regions, circle of radius 3, circle of radius 1. Now notice that both of the regions are going to be counterclockwise, so that's good. All right. And what we're looking for is we're looking for the region that's going to be bounded by that. So we're having two line integrals, and it looks like that ultimately we're going to basically get the region in between there. We know that P is going to be x cubed minus y cubed. We know that Q is going to be x cubed plus y cubed. All right. Now we're going to take the partial of Q with respect to x, and that's going to be 3x squared. We're going to take the partial of P with respect to y, and that's going to be a negative 3y squared. We're going to change this from our original line integral, and we're going to turn it into a double integral now. Okay, so now remember, this is a closed region, so we could write it like that, not that we have to, of x cubed minus y cubed dx plus x cubed plus y cubed dy. And we can turn that now into a double integral. Right, so that's going to be double integral. Now I'm just going to say r for right now, and I think most of you know where this is going. 3x squared minus a negative 3y squared dA. Right. Clearly we can factor out a 3, and we can write that as x squared plus y squared, and this is just begging for us to use polar coordinates, and we know polar because it's two circular regions. All right. In fact, it makes it very easy for us to write as polar, so I'm going to factor out the 3. Remember, the two circles were of radius 1 and radius 3. We're going all the way around both circles, so 0 to 2 pi, all right, and the 1 to 3, make sure it's between there. And then we just have x squared plus y squared, which is r squared, and we always have that multiplier r dr d theta. At this point, the rest of it's elementary. All right. So 3 integrals 0 to 2 pi d theta times an integral from 1 to 3 of r cubed dr. We know that this just turns into 3 times 2 pi from this one, from this first integral, times r to the 4th over 4 from 1 to 3. So we still have that 6 pi. I'm going to hold on to 6 pi. So we have 6 pi. I'm just going up here to finish this off. We have 3 to the 4th over 4 minus 1 to the 4th over 4. All right. And I believe that becomes 80/4, which is 20. 20 times 6 should be 120 pi. And let me verify that with my calculator, even though I shouldn't have to. All right, so that's really nice that we were able to evaluate very quickly using our polar coordinates and Greene's theorem. Okay, if we go all the way back up here, if we were to use a parameterization just to get an idea of this, well, x would have to be, you'd actually have to do 2. So the first would have to be, x would be equal to cos theta. You'd have to do 2 parameterizations. Y would have to be sine theta. And then for the second, this would be path 1. And then for path 2, you would have to say x is 3 cos theta, and y would be 3 sine theta. All right? So clearly, Greene's theorem is much easier to utilize than those parameterizations. All right.